When we focused on higher order differential equations, the only type of problem that really we gave much effort to solving were constant coefficient problems, where we had maybe a times some y double prime plus b times some y prime plus c times y equals some function, but the a, b, and c were all constants. What if they aren't constants? Well, we only saw really one type of equation. So, for example, recall that equations of this form, so we had some that looked like this. Maybe like ax squared times y double prime plus bx times y prime plus c times y was equal to 0. And notice in this case, we've explicitly put coefficients of the y double prime, y prime, just those two terms in this case, that aren't just constants. They have, in this case, polynomial terms, x squared and x. And we did a couple of examples where we could kind of intuitively work our way through, recognize that these types of solutions tended to take the form of polynomials. So equations of this form had solutions of the form like y equals x to the nth power, something like this. We did a couple of examples like this, and the idea is that as you take more and more derivatives of x to the n, the power decreases each time. So when if I were to plug in y equals x to the n for this term would have a total power of x to the n. When I plugged in y equals x to the n into this term, well, I would need to take a derivative of y, so I'd get nx to the n minus 1. The power would be n minus 1, but this extra factor of x right here would make up for it and make this term also have, in total, a power that looked like x to the n. And then similarly for this term, we'd take two derivatives, so the power of x in that case would be n minus 2, but that n minus 2 would be compensated for by the x squared that we have sitting here. So we had solutions of this form. I want to basically kind of take the intuition that we learned from this case and apply it to cases where we don't have this perfect pairing where, as you go to higher and higher derivatives, you also go to higher and higher powers of x. So basically, what if those coefficients were not only not constant, but also didn't follow this pattern of increasing powers of x? So in this case, what if the coefficients don't increase in power with increasing derivative? So there's a whole bunch of problems of this forms, things like this. So example being, what if I had a problem that looked like this? I have something as simple as y double prime plus xy equals 0. Or maybe something more complicated. Maybe it's like x squared y double prime plus x y prime plus some other x squared term again with y equals 0. And so notice, again, we're not going to be able to just plug in x to the n and count on the derivatives decreasing the power of n and the coefficients compensating for that, because over here, the coefficient of this one won't match the coefficients of this one. We aren't going to get quite what we're looking for. So these are the examples of things that I'm talking about, types of problems that we don't have solution methods for. So right now, we don't have good methods to solve these. Well, one approach that we are going to be able to take to solve many of these types of problems is using what we call series solutions. So it turns out, are polynomials still a good guess for the solutions? Right, so we guessed a polynomial x to the n for this equation. Are polynomials still a good guess here? And the answer is yes-ish. Right? It would make sense that polynomials would work in some of these problems because, again, if we plug in polynomials for y, then y prime will be a polynomial, y double prime will be a polynomial, and at least these will all be polynomials of the same class of functions. But the idea is we can't just pick something this simple anymore. Instead, we're going to guess infinite polynomials, essentially power series solutions. So if we use a solution, or guess, I should say. Really, I should say guess. If we guess a solution of the form, this is going to be important, y equals the sum from n equals 0 up to infinity of some coefficient, Cn, times x to the n. If we guess solutions of this form, what this really is an infinite series. So essentially an infinite polynomial, right? So i.e. an infinite polynomial. Or infinite series. Then we'll be able to find solutions. Find solutions. Okay. So I'll give you some insight into exactly what that's going to look like in a minute, but I want to give you a few quick pointers to try to help you refresh a little bit about what power series are, what they look like, and what some of their properties are. So, properties are just, even in this case, facts of power series. And if you want a more in-depth refresher, I would recommend looking in section 6.1 of our book. They go into a bit more detail, but I'm just trying to pick out the absolute most important pieces that we need. So the main thing is really the whole point in Calculus 2 of talking about power series was to build up to Taylor series. And the point of Taylor series was that you could basically represent functions like exponentials, logarithms, sines and cosines as infinite series, as power series. So first things first, power series are functions and they can be used to represent functions. So, and in particular, like non-elementary functions. Things like those ones I just mentioned, sines, cosines, exponentials, logarithms, etc. Square roots, radical functions as well. There was a whole big deal made in Calc 2 about convergence. And so one thing I want to also remind you is that power series don't necessarily converge. And even if they do converge, they don't necessarily converge everywhere. They may only converge on a certain interval. So they may not converge everywhere. Or even anywhere, but that won't be terribly useful if it doesn't converge anywhere. And one of the most useful ways that we tested for convergence, there were a bunch of tests, but for power series in particular, the ratio test was one of the main tools that we used. I'm not going to quiz you on that here, but if you want a refresher on that, go back and look at the ratio test for power series. And one other thing that's important is we can apply all the normal mathematical operations to them. So you can add power series, you can multiply power series, you can integrate them, you can differentiate them. So they can be added, multiplied, divided, but you could, in a sense, that's really, really ugly, but it's possible. We're not going to need to do it, so I won't even mention it in writing here, but they can be integrated, and differentiated. And we are going to be adding these things, and we're going to be differentiating these things. So these two in particular are things that we're going to actually do. So with some of these properties in mind, I want to think about what it means when we differentiate power series, because really these are going to be the hard parts of these problems. These problems are straightforward. In fact, they're going to be very similar to the method of undetermined coefficients that we did before, but we're going to need to be adding a bunch of infinite series and powers, basically adding power series, and we're also going to need to be differentiating power series. So let's do this. So with this in mind, let's look at some differentiation. And I'll do it for us here because really, once we do this set of cases, these are the only cases that we're going to need. So if we have y equals the sum from n equals 0 to infinity of Cn x to the n, then what does y prime look like? Well, the derivative y prime, when you take the derivative of a polynomial, you do it term by term, even in this case if that polynomial never terminates, right? If it's an infinite series. So basically you can differentiate term by term. These are what the individual terms look like. So if I were to differentiate this, right, x to the n, the derivative of that, the n would come down and the power would decrease by 1, and the derivative would look like this. So we're still going to have a sum from n equals 0 to infinity. That coefficient Cn isn't going to be changed, but we're going to pick up nx to the n minus 1. That is the derivative of x to the n, right? The n comes down and becomes a coefficient in front, and the power goes from n to 1 less, n minus 1 in this case. What I want to mention is, in this case, we'll often rewrite this in the following way. We're going to actually write this as the sum from n equals 1 to infinity of Cn times n x to the n minus 1. And why am I allowed to do that? The only difference, if I can point it out to you, is that we changed the index of our summation. This one started at 0, this one starts at 1. But I didn't touch any of the rest of this, so why was I allowed to do that? Well, the reason I'm allowed to do that in this case, because over here, what happens if we were to plug in n equals 0? So I'd have c sub 0 times 0 times x to the negative first power. And this 0 right here basically kills off that first term. And so we might as well leave it off. So basically, we can ignore the n equals 0 case because this term will be 0 and the whole thing will be 0 anyways, right? So we can do this because the whole thing, it's 0 when n equals 0. So that's why we could ignore that first term. What about for the second derivative, y double prime? Well, we're doing the same thing. So I'll start over here. We have the sum from n equals 0 to infinity. And I need to take two derivatives of this now, which is another way of thinking about it, of taking another derivative of this, right? So if this is the first derivative, if we take the derivative of that, that'll give us the second derivative. So I'm still going to have my Cn. I'll have that factor of n sitting down there. And now when I take the derivative of x to the n minus 1, I'll pick up a factor of n minus 1, and we'll wind up with x to the n minus 2 as the overall power. And this also can be rewritten as the sum from n equals 2 to infinity of Cn times n minus 1 times x to the n minus 2. So up here we were able to basically ignore the first term and just start our index at n equals 1. Down here we're going to be able to ignore the first two terms and start at n equals 2, because if n is equal to 0, this term will be 0 and kill the whole thing off. And if n is equal to 1, then this term will be 0 and kill the whole thing off. So we can really start at n equals 2 because these other two terms will both be 0. Okay, so for the same reasoning, because it's 0, let's do it over there, 0 when n equals 0 or 1. So we can start at the index 2 instead. So basically, this piece right here, this piece right here, and this piece right here are going to be important. These are going to show up in essentially every problem that we're going to do once we actually start applying this method to solving these non-simple, trivial differential equations up here, things that look like that. Okay, so that's what we're going to take a look at. Okay, so basically, we'll simply plug these expressions into the ODEs and solve in a similar method to the method of undetermined coefficients. Remember, that was for solving for the particular solution of a second order differential equation or higher. This is going to just to solve for the general equation, but the approach is going to be very, very similar. So solve in a similar method to that for the various CNs, so to speak. Right. The idea is we're trying to represent a function like this as a power series. The thing that uniquely defines a given function when it's represented by a power series are just which coefficients we pick here. Right. So, for example, if you're trying to find the power series representation or the Taylor series representation, alternately calling it that, of a cosine function, because the cosine function is even, turns out all the odd powers of x are missing. So you wind up with 1 minus x squared over 2 plus x squared over 4 minus x to the 6th over 6. And I should say those denominators should have all had factorials. So over 2 factorial, 4 factorial, and 6 factorial, and so on. But basically you wind up with stuff that looks like that. And all that uniquely determines that function are those coefficients, right? A bunch of 1, 0, negative a half, 0, positive a fourth, or 1 over 4 factorial, whatever, and so on. So really, it's just the C sub n's that we need to figure out. Okay. So this is the hard part, though. When we plug these in, we're going to need to basically be adding up, right? We're going to plug in series for in place of y double prime, in place of y, in place of y prime. And we'll have a bunch of different series that we'll need to combine into one big series. We're going to have to be able to add them together. And that's where the difficult things come into effect. So the hard part will be basically combining the series together. And so just a couple of quick tips for doing this. What we're going to want to do, maybe I can even label these tips. So tip number 1, we really want to make them all start. So if we have a bunch of different series, make them all start with the same power of x. And so what I'm saying is if one series starts with like a constant, 1, and another one starts with x, you don't want to treat them like that. You want to make them start in that case, both with x, and that constant that only showed up in one of the two terms should be pulled outside of the series. So basically, pull any other terms that aren't, so basically any terms that don't show up in both, pull them outside of the series so that we can make the two series look the same, start at the same value. So pull any other terms out of the series. So out of this sum. Tip number 2, we're going to shift our indices of our sum in order to sync them. And This will make more sense when we do it, but basically I don't want to have one sum that starts with n equals 0 to infinity and another sum that starts at n equals 1 to infinity. I want to find a way so that they are synced, so that they both start with the same index as well. That's what I mean when I say shift indices. Find a way to write them with the same count on the indices. And then after you've got both of those, then we can combine terms. So this is, I'm calling it tips. It's really almost more the process. Maybe that would be better phrasing. So the general process for doing this is you do those two things, then you can combine them, right? So, okay, I think we're good. Okay, so let me just do a real simple example of how we could solve, for example, a first order differential equation. One that we already know how to solve, but doing this one will give us kind of a sense of what the process is going to look like. Then we'll up the difficulty level and try a problem that is more like these ones up here. Looks more like one of these that we don't have a solution to yet. Okay. So for now, let's do something simple. Let's say I want to solve y prime plus y equals 0 using power series. Right, this is a first order differential equation. It's linear. We could simply use integrating factor on this. So as a side note, right, we're just doing this to kind of get a sense of how this process works. There's easier ways to do this. This can be done easily using integrating factor. And the solution to something like this winds up being like exponentials, right? Essentially, we're saying I want to find, in this case, I guess, negative exponentials. I think we're going to get, yeah, right? So if y was e to the negative x, then y prime will be negative e to the negative x. We'd add them together and get 0, right? So we get something like this. Y equals some constant times e to the negative x. Right, that's what we should wind up with here. Okay, so that's what this would look like. So all we need to do is try y equals the sum from n equals 0 to infinity of Cn x to the n. This is always our starting point, right? We are going to start with this as our guess, right? We're going to assume that this is the form of our solution. If this is the form of our solution, in this equation we have both y and y prime, so I'm going to also need y prime. While we're at it, let's write that down here. We know y prime is going to be equal to the sum from n equals 1 to infinity of Cn times n x to the n minus 1. So here's this. Again, you don't need to do these, make it hard on yourself each time. Just use these expressions right here that we've already underlined. We've already done the work. So I have this one, I have this one. Jump straight to them. Don't waste your time trying to recompute this every time carefully. Just more or less memorize these. Okay, so there are those two values. We just need to now sub them into the ODE and then try to solve for those values of C sub n. So the first term is y prime, so that's this one, plus y, so plus this one, equals 0. So that's what I'm going to get. I'm going to get the sum from n equals 1 to infinity of Cn times nx to the n minus 1, there's the y prime term, plus y, so the sum from n equals 0 to infinity of Cn x to the n equals 0. This term is our y prime, and this term is y. Y prime plus y equals 0. And here's what I meant when I said that the difficult part is now going to be combining these into a single expression, basically into a single summation. So the first thing we should just check, just to make sure, is that both of these start with the same power of x. So in this one, when I plug in n equals 1, what is the power of x that I get? So when n equals 1, I'm going to get x to the 1 minus 1. So x to the 0th power. I'm just going to get a constant from this term. So the first term of this sum is a constant. Let's check this one. Well, this one I just plug in n equals 0, and clearly I will get x to the 0. So this one is also a constant. So checking our process up here, these ones luckily already start with the same power of x. There's the word that I'm missing there. This is x to the 0. This is also x to the 0 in the way that they're written. So this is already done. So we're good to go here. I don't have to pull any extra terms out. On to step number 2. Now I need to make sure that I shift the indices to sync them. And right now I can see that they are not synced. Right? This one starts at 1. This one starts at 0. Let's shift the indices to sync them. To do that, what we're going to do is take a look at these and introduce a new variable name. So I'm going to call it k instead of n. And over here, it's going to be easy. I'm going to let just k be equal to n. So in this case, they can both just start, that I can still start it at, in this case, k equals 0 instead of n equals 0. But over here, if I want to make this one start at 0, then I need to make k be equal to 1 less than whatever n is. So basically n minus 1. Now, when I plug in the first term over here, n equals 1, what value of k does it give me? So when I plug in n equals 1, I plug a 1 in right here, I have 1 minus 1, and k will start at 0. Just like over here, k starts at 0 because k is equal to n and starts at 0. And you'll notice a pattern as you do these. Basically, the power up here tells you what you should let your k be equal to when you do these, right? In this case, k equals n minus 1. That's the power sitting right there. Here it's k equals n. There's the power sitting right there. And by doing this, it'll allow us to shift and sync these two separate pieces. So if in this case, if k is equal to n minus 1, then if I were to solve for n, I'd have to add 1 to both sides. I get n equals k plus 1. Over here, n equals k equals n. I don't need to do an extra algebra step. I've already got k and n solved for on this side. Okay, so let's see what this does for me over here. This term basically isn't going to change because I didn't actually need to shift the indices. The only thing that's going to change is what I'm calling our index. I'm not calling it n anymore. I'm going to call it k so that I can use that k index in both of these two sums. So this one's not going to change. I'm just going to have the sum, but now from k equals 0 to infinity of ck x to the k. And I'm still going to have the whole thing be equal to 0. So this hasn't changed. I'll pull that down. This hasn't changed, other than we're calling it k instead of n now. But this is going to change. Over here, again, when n is equal to 1, what is k equal to? So when n is equal to 1, which is our starting point, k is going to be equal to 0. So that's the whole point of it, is now this allows me to start at k equals 0 and do my sum to infinity. So they both now are the same summation, starting at the same index. How is that going to change all of this stuff in here? Well, the c sub n term, writing that in terms of k, well, n is k plus 1, so I can rewrite that coefficient as, I can rewrite that coefficient as c sub k plus 1, because that's what n is. C sub n, where n is equal to k plus 1, can be rewritten as c sub k plus 1. Similarly, n is a factor of k plus 1. And then x to the n minus 1, I have x to the n minus 1, but what was n minus 1? N minus 1 was k. And there's what this winds up looking like. So now I have these two different sums, but they're synced. The sums are synced, and so I can group them into a single sum now. I can rewrite this as the sum from k equals 0 to infinity, and now I can kind of group all the terms. They're both going to have an x to the k power, so I can factor that out, and we'll wind up with c sub k plus 1 times k plus 1 times an x to the k plus c sub k times x to the k. So I'm basically grouping these together, factoring out the x to the k term, and grouping these coefficients together in one place. And that whole thing is equal to 0. And so here's the setup that I have. My goal, again, is to figure out these C's, right? The whole point in determining what the infinite series looks like that gives us our solution is to figure out the coefficients. That's what uniquely determines a given power series, are the coefficients. So I need to solve for the coefficients. Based on the equation I have set up, this needs to hold true, right, for every value of x in the domain of the problem, right? We're still solving this with x being our independent variable. And if this needs to work for every single possible value of x, that needs to work for when x is equal to 1, 2, 3, any number in our domain. All that's telling us, the whole point of that is to tell you this is not the term that must be making the whole thing 0, right? The only way to make this term 0 all the time is to force x to be 0, but it needs to be true at all the values of x, not just at x equals 0. So if this isn't the part that's making the whole thing 0, then it must be these coefficients. For this equation to be equal to 0, for this infinite sum to be equal to 0, all these coefficients better be 0. And so that's what we wind up with. This is the equation right here, that this has to be equal to 0. So we know that basically c sub k plus 1 times k plus 1 plus c sub k has to be equal to 0. And what we can do is solve this for whichever power or whichever subscript is the larger one. So k plus 1 is bigger than k. So I want to solve for c sub k plus 1. And by doing that, I would need to subtract this off to the other side and then divide by the k plus 1. So I'm going to get negative c, in fact, let's write it this way, negative 1 over k plus 1 times c sub k. So again, all I've done is move the c sub k over to the other side, so it now has a minus sign, and then divide by k plus 1. And I get what's called a recursion relationship. If you know a given current value, c sub k, you can use that to figure out the next value of c. So if I know c sub 0, I can use it to figure out c sub 1 by letting k be equal to 0 in both cases. Once I know c sub 1, which I found by knowing c sub 0, I can plug in c sub 1 here to get c sub 2. Once I know c sub 2, I'll plug c sub 2 in here to get c sub 3. And we can generate these coefficients systematically through this, what is called, again, a recursion relationship. Okay, so let's actually do that, right? This has to be true. The presumption here was that this was true for k equals, right, 0, 1, 2, yada, yada, yada. So this is for k equals 0, 1, 2, dot, 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 and so on and so forth. So all we need to do is take a look at this and plug in these values. So let's start with k equals 0. If k equals 0, what it'll tell us is that c sub 0 plus 1, so that's going to give us that c sub 1 must be equal to negative 1 over, again, plugging k equals 0, I'm going to get a 1 in the denominator, times c sub 0. So all I did was plug in 0 here, here, and here. And it gave us this relationship, which simplifies a little bit to just c1 is negative c0. So whatever c0 is, c1 is the opposite of that. Then we can go to k equals 1. When k equals 1, I'll plug in 1 in all of these locations, and I'll have what c sub 2 is in terms of c sub 1. So c sub 2 is going to be equal to, again, plugging in k equals 1, negative 1 over 2. So negative 1 on top, 2 on the bottom by plugging in k equals 1, times c sub 1. But that's equal to, so that implies that c2 can be written back in terms of c1, which could be written in terms of c0. It's going to be equal to positive 1/2 of c0. Right, the sign flipped because I basically took this c1 equals negative c0 and replaced this term right here with the negative c0. And so now I have c2 in terms of c0. And then we can keep going. K equals 2. The k equals 2 case will allow me to figure out what c3 is. And c3 is going to be negative 1 over, again, we're plugging in k equals 2, so C3 equals negative 1 over 3 times C sub k, but C sub k when k equals 2 is C sub 2. But C sub 2 is a half times C sub 0, so now I'm going to get negative 1, let's do it like this, negative 1 over, I'm going to have a factor of 3 from right here, so here's my negative 1/3, times, I'm going to get another 2 in the denominator from this 1/2, times C sub 0. And so on and so forth. So we could continue this indefinitely, yada, 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 yada. Oops. This whole thing that I just solved for, let me just move it, is what you get for C sub 3. I left that part off. So C sub 3 was equal to this. But plugging in this for C sub 2 into this location gives us that C3 looks like this in terms of C sub 0. And we can continue this, and what you basically have is that C sub 0 can be thought of as the arbitrary constant of integration. C sub 0 is like the arbitrary constant of integration. And what we've essentially got when we think about this is that our solution, takes the following form. So again, just generically speaking, this is the form of our solution. But when we now plug in the specific C sub 0, C sub 1, C sub 2, and so on that we found through this recursion relation, what happens when we plug in our C sub 0? So basically plug in our first term, x to the 0 is a constant, it's just 1, and we'll have C sub 0. Plus, now let n be equal to 1, we'll get C sub 1 times x to the first power, right? So C1x plus C2x squared plus C3x cubed plus dot, dot, dot. Right? That's all this summation is supposed to look like. But we already know what all of these are. So this is going to be equivalent to C0 plus C1 times x. But what was C1? C1 was negative C0, so negative C0 times x. Plus C2 times x squared, but what was C2? Well, it was 1/2 C0, so plus 1/2 C0 times x squared. Plus C3 times x cubed, but what was C3? Well, it was negative 1 over 3 times 2 times C0, x cubed, and so on and so forth. And we can kind of simplify this and recognize that C0 is showing up in every single one of these terms. So let's factor that C0 out. And I'll just have 1 minus x plus essentially 1/2 x squared minus 1 over 3 times 2. Let me keep it written like that. 3 times 2 times x cubed. And if it's easier to see, I could think of this as really a 2 times 1 and a 3 times 2 times 1 and so on, plus dot, dot, dot. And recognize that what I'm getting here, this over here is taking the form of, so we've got our C0 times the sum from n equals 0 to infinity of essentially x to the n, that's giving us the powers that we want, but what about the coefficients? Well, it's switching signs each time, so it's really negative 1 to the n, flipping signs each time, and we're also picking up an n factorial in the denominator, right? So the denominator of this one is 1, which is 0 factorial. The denominator of this one is 1, which is 1 factorial. The denominator of this one is 2, which is 2 factorial. The denominator of this is 3 times 2 times 1, which is 3 factorial. The next one will be 4 times 3 times 2 times 1, which is 4 factorial. And this is equal to, if you remember your Taylor series, this is the Taylor series for e to the negative x. That's what this is. If we didn't have the sign switching, the negative 1 to the n, You might be more familiar with that one. That's e to the positive x. So if the sign wasn't flipping, if they were all positives, we'd have e to the positive x. But in this case, we get e to the negative x because the sign is flipping each and every time. So that's the idea. This is the solution that we would have gotten, again, using integrating factor, doing this problem the easy way over here, c e to the negative x. Well, sure enough, that's what we found. Some constant times, in this case, an infinite series, a power series, that represents e to the negative x. And in general, you won't always get a power series that represents a specific function, right? Sometimes you'll just have a power series that isn't a well-known, isn't the well-known Taylor series of a given one of these types of functions. And most of the solutions to problems like this aren't going to have a nice e to the negative x type solution or just a polynomial. They're just going to be the power series. So that's going to be as good as it gets. Okay, so let me mention a couple more things, but this is going to be the process of doing this. Let me just mention a couple of other things. So things to keep in mind. Let's see here. Let's keep in mind number one, when we're talking about a power series, you have to center it somewhere, right? We have to center a power series. You may not remember this, but all the power series we dealt with and all the Taylor series had to be centered at a specific value, at a constant of our choosing. At a chosen point. For the ones that I'm going to care about, that we're going to care about, it's usually going to be 0. So often x equals 0, but more generally, it could be x equals a or x equals x naught. Oops. X equals some arbitrary point. And if this was the case, if we picked x naught, what we would have is that instead of y being equal to the sum from n equals 0 to infinity of cn x to the n, it would be x minus x naught to the n. This is what we mean when we say centered at x naught. For all the examples that we're going to do, we're going to only focus on centering it at x equals 0. So we won't have this extra term here. This point that we're centering it at, so this point at the center, can be a couple of different things. It can be what we call ordinary, which is what it sounds like. It's just an ordinary point. Or it can be singular. And this is also a term you've hopefully heard in the context of a math class. Basically, ordinary is normal. Singular is essentially we're dividing by 0 somewhere at that point. So ordinary is what it sounds like. But singular means we're dividing by 0 at that point. So when I say dividing by 0 at that point, where are we dividing by 0? The idea is in the ODE. So for example, if we put it in standard form, if we put the ODE in standard form, which is y double prime plus p of x, y prime plus q of x times y equals 0, right? This is the form that we've often used. If either of these are singular at any points, right? So something, for example, so if these functions are singular, then at any points, right? At any points, those points are what we call singular points. Right, so for example, I called this an example, but I didn't really do a very good job of that. So let's not call that an example, let's call this an example. So to be more explicit, what if I had this, xy double prime plus y equals 0? Well, it looks fine, but it's not in standard form. Standard form requires the coefficient of y double prime to be 1. So we would have to rewrite this in standard form as y double prime plus, dividing everything by x, 1 over x times y equals 0. So in this case, this is our q of x is singular, at x equals 0. So x equals 0 in this case is a singular point. We can deal with problems like this. It turns out they're just a little bit trickier, and we're not going to worry about them. But it is something to take into consideration. So they can be dealt with if you want to. So these are dealt with in 6.3 if you'd like to read up on it on your own. But we're not going to worry about that. We're going to stick to ordinary points. So points where there is no singularity to worry about. The last thing that I want to keep in mind, because I think we had a bullet pointed list going at some point. Yes, so bullet point 1, bullet point 2, down here is bullet point 3. Bullet point 3 is that, again, power series don't always converge everywhere. So the power series that we find for our solution may not converge everywhere. Right? So we found a solution, but that solution isn't necessarily valid everywhere. In fact, it will only converge on an interval that looks like this. So basically a distance r away from the point that we center it at. So r is the distance from the centering point, x0, to the nearest singular point. Which may even be imaginary. So even if you have no real points that are singular, but if there's a point in the complex plane that turns out to be a singular point, you're still going to have convergence issues if you go too far from the point that you're centered at. So that distance is going to play a role. So again, for us, that's not going to be a big deal. I don't want to focus a ton on all these singular problems. Let's focus on differential equations where these singularities aren't an issue. But if you want to take a look at 6.3, the approaches are more or less the same. They're just a few extra subtleties that I don't want to waste time on. So let's do a problem. So with that said, let's do this. So we're going to deal with a problem that does not have a singular point. If you're trying to expand your power series about a singular point, again, things get harder. There are some good examples in the book, so I'm going to do a different example than the ones in the book, so you have some extra examples to look at if you'd like. I think they do about 3 of these. It's going to be similar to this process, but I want to do problems that look more like, again, the ones that we were looking at here. Right, so they do this one, for example, in the book. So I'm not going to do that one. You can take a look at it. They do a couple other ones as their examples. So utilize the book for extra examples, because otherwise this is the only example I'm going to do to help you with your homework. So let's say I want to do this one. Let's do y double prime minus xy prime plus 2y equals 0. So, and I want to find the power series solution. Let me write it explicitly. Find power series solution about, so centered at x equals 0. Right? X equals 0 is not a singular point. We are not dividing by 0 at any of these coefficients at any point. So the radius of convergence of this thing is going to be infinite. When we find the solution, that solution is going to converge everywhere because there are no singularities in this equation. So we're going to do the same thing. We are going to let our y be equal to the sum from n equals 0 to infinity of Cn x to the n, which will automatically give us that y prime is the sum from n equals 1 to infinity of Cn times n x to the n minus 1. And y double prime, again, I'm basically doing these without thought. We basically have these memorized because they are always going to be the same. N times n minus 1, x to the n minus 2. And so we're going to have to plug these all in, check to see if that they all start with the same power of x. Once we verify that that's the case, or correct it so that they do start with the same power of x, then we will need to re-index them so the indexes all match. So that's going to be our goal. We can then combine them into one. So plug these or sub these into the ODE. So when I plug these into the ODE, the first term is just y double prime, so that's going to be this whole thing. So we're going to get the sum from n equals 2 to infinity of Cn n minus 1 x to the n minus 2 minus xy prime. So minus xy prime is the next term. So minus x times y prime is this sum. So minus x times y prime looks like this. So here's my minus x, and this sum is the y prime, plus 2y. So plus 2 of, here's y. And that whole thing is supposed to be equal to 0. And so let's just check what each of these is going to be equal to if we were to plug in basically the first term. So when we plug in n equals 2 here, in that case, we are going to get an x to the 0th power. So it's going to be a constant. The first term of this sum is a constant. When n equals 2, and I plug in 2 right here, we get a 0th power. X to the 0 is a constant. Similarly over here, when I plug in n equals 0, we're going to get x to the 0. This one also starts with a constant in this sum. And this one here, when I plug in n equals 1, 1 minus 1, I get a constant, except that I have an extra factor of x out here that needs to be incorporated into the sum, right? I need to put that x into the sum. So if I were to rewrite this, the first term I wouldn't touch, and the second term, and the last term I wouldn't touch. If you can do this step in your head and you don't want to have to write out as many lines and copy as much stuff as I'm doing, that's fine. But this one, if I move that x inside, I really have Cn n x to the nth power. Right? By moving this x inside the sum, all it's doing is raising the powers of x by 1. So instead of n minus 1, it's just going to be n, but otherwise it's identical. So I've rewritten this term, moved the x inside, and this is what it looks like. The power of x is just higher by 1. But now we can see when I plug in n equals 1, the first term of this sum, I get x to the first power, whereas the first terms of each of these was x to the 0. They were constants. So this term this one starts with x, these ones started with constants. So I need to pull out the constants from these so that all three terms start with x. We always have to start with basically whatever is the kind of highest power of x that's common to all of them. Sorry, not highest. The lowest, that's what I'm looking for. There's the wording. The lowest power of x that's common to all of them. So in this case, The lowest power of x here is x to the 0, but x to the 1. So the lowest one that shows up in all is x to the first power. The second term of this will be x to the first power. The second term of this will be x to the first power. So let's pull out all the other terms that aren't x to the first power. In this case, that's going to be the n equals 2 term. So I will get c sub 2. So this is our next step. Our next step is I'm going to get c sub 2 times 2 times 1 times x to the 0. So that's the constant term from here. Again, I just plugged in n equals 2 here, 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 and here, and got this expression. This one doesn't have a constant term, so let's skip to this one. When I plug in n equals 0, we have our factor of 2 out here. I'm going to get c sub 0, x to the 0. So c sub 0, x to the 0. There's a constant term. So those are the constants. And what remains is the following. So this one's going to be now the sum from n equals 3 to infinity of cn n times n minus 1 x to the n minus 2. Right, all I've done is I explicitly evaluated the n equals 2 case and pulled that out separately because it wasn't basically an x to the first power term. So there's that one. Basically, if you think about it, this piece I broke into this piece plus this piece. This piece I didn't touch. It already started with x, so we're good there. And hopefully that was clear enough, right? So this one was, let me sneak some arrows in here. Let me finish writing what I'm writing, then I'm going to come back and sneak some arrows in to hopefully make this unconfusing in case it was confusing for anybody. So there's that term, haven't touched it. And then the last term is whatever we can move that 2 inside, it doesn't matter. The sum, but now this one starts at n equals 1 to infinity of 2cn x to the n equals 0. So this term here in blue got split up into this part and this part. And the whole point was because this one is basically x to the 0 when n equals 0, but this one was x to the first power at its first index when n equals 1, right? This one started at 0, so that was our first place. This one starts at 1, and we got a different power of x. And then this one is x to the 0 when n was equal to 2, so for its first term. And that's how I recognize that really the first term of this one's a constant, the first term of this one's a constant, but the first one of this term of this one is proportional to x to the first power. And so I pulled out the constant here and the constant here separately. So now all of these 3 pieces all start with x. Good. So now I've got these sums. They all start with the same power, in this case x, but we also need to re-index them because they all start at different indexes. So I'm going to use the index. Again, I'm just going to go look at the power and have that tell me what my index change should be. So for this one, I'm going to let k be equal to n minus 2. For this one, k is just going to be equal to n, and for this one, k is going to be equal to n. And again, I'm just looking at the powers, n minus 2, n minus 2, n, and let me write what I mean. There we go. N, 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 n. So this is the one that we now have to solve for n by adding 2 to both sides. N is equal to k plus 2. And we can rewrite these. So again, I'm not going to touch these first terms. I guess I'll clean them up a little bit. Right, x to the 0 is just 1, so this is really just 2c2. And this one is really just 2c0. Plus this one, when we re-index everything, it's going to start off now. When n is equal to 3, what's the value of k? So when I plug in n equals 3, k is equal to 1. So it's the sum from k equals 1 to infinity. And c sub n becomes c sub k plus 2 times n, which is k plus 2, times n minus 1. N minus 1 is 1 less than n. If n is k plus 2, then 1 less than that is k plus 1. So n minus 1 become k plus 1 from that variable change. And then x to the n minus 2 is x to the k. So there's what that term looks like. Minus the sum from k equals 1 to infinity. In this case, k and n were the same, so I can just rewrite these, swap every n out for k. So c sub k times x to the k. Same for the last term. K equals 1 to infinity, 2c sub k, x to the k. And that whole thing is supposed to be equal to 0. It's just a bunch of ugly algebra, so let's group these ones together. I got c2 plus c0, factor the 2 out, there's our constant sitting out front. And now comes our single sum. I'm going to combine these all into a single sum. K equals 1 to infinity. They have the same index, and they all start with k to the first power, or sorry, x to the first power. And so I'm going to group them all together, factor out the x to the k, and we will get c sub k plus 2 times k plus 2 times k plus 1. I'm going to get a minus c sub k times k. And I'm going to get plus 2c sub k. All of those times the x to the k term. So I basically combined them all into a single sum and factored out the x all in one step. So we've got c sub k. It shows up in these two places. We can kind of simplify in a minute, but the point is this whole thing, again, I left this off, is equal to 0 according to the original differential equation. And if it's equal to 0, we have basically a polynomial here that's equal to 0. It happens to be an infinite polynomial, but it's equal to 0. That means every single power of k has to have a coefficient equal to 0. So this polynomial needs every power of x, right? X to the 0, x to the first, x to the second, so on and so forth, equal to 0 for this equality to hold. And hopefully that makes some sense, right? It's basically, again, the process that we used when we did method of undetermined coefficients. It's the process that we kind of use often when we do partial fraction decomposition and look at all the different orders of x. In this case, we've got a 0 to match every single term to, so every single coefficient needs to be 0. These constants need to be 0. So it tells us that basically c2 plus c0 times 2, that coefficient, there's our constant, right? This is our x to the 0 term. Our order x to the 0 term needs to be 0. And then all these other terms, which are all the coefficients of all the various x to the k's, also need to be 0. So order x to all the powers greater than 0, x to the n greater than 0. All of those, this is the coefficient. And that coefficient is ck plus 2 times k plus 2 times k plus 1. Let me group these together and factor the c sub k out. So plus c sub k times, what is the factor? I got a negative k factor for one of them, a positive 2, so that is 2 minus k is the factor. That also has to be equal to 0. So this needed to be 0, and this needs to be 0. And we get these two separate equations here that we can use. This one is going to give us our recursion relation, and this one gives us a relationship specifically between C0 and C2. So this first one right here tells us that basically for that sum to be 0, C2 needs to be the opposite of C0. C2 and C0 are opposites of one another. From this one, if we get our recursion relationship for the larger value or the larger index, so that's going to be the ck plus 2 term, I need ck plus 2 in terms of the rest of it, in terms of c sub k. So I'm going to move this over to the other side. So when I subtract this over to the other side, I can flip the sign of this. Instead of carrying around an extra minus sign everywhere, I'll just call it a k minus 2. We've got our c sub k. And then we have to divide by the other coefficients over here. So if you don't follow the algebra I'm doing here. That's all it is algebra. You can do these steps more carefully. Subtract this term over to the other side. What you'll be left with is this stuff. Divide by this. Then correct, multiply that negative sign we wound up with when you move that over to the other side through. And you should get this expression over here. So here's our recursion relation. But what I want you to notice here, it's a little bit different than that example we did before. Remember, the first example we did back here of the first order differential equation, we only wound up with, in this case, a c sub 0 with one constant that was kind of undetermined. In this case, our recursion relation has essentially two constants that aren't really determined, and we can kind of see this as we go forward. We have a recursion relation right here that's going to tell us how ck plus 2 relates to ck. So when I let k be equal to 0, it'll tell me what c sub 2 is, but I already know that relationship right here. When I let k be equal to 2, so c sub 2, it'll tell me what c sub 4 is equal to. But notice, as long as this one is even, we're going to be adding 2 to it and getting another even number. So each value that we know, and use this recursion relation, it skips over the k plus 1 terms in between. So basically, I'm going to generate one list of all the even c sub whatevers, c sub even numbers by starting with 0. If I start with 0, I can get 2. Once I have 2, I can get 4. Once I have 4, I can get 6. And that's going to give me one set of solutions that I need. Basically, it's going to give me one of my solutions. But I can also start with C1. What if I let k be equal to 1? When k is equal to 1, k plus 2 over here will be equal to 3. So if I start with C1, I can get C3. Once I have C3, I can get C5. Once I have C5, I can get C7. So I'm going to have one recursion relationship that generates all the even numbers, one that generates the odds, and those two separate things. One's going to be in terms of C0, one's going to be in terms of C1. Those two separate pieces are going to make up my two linearly independent solutions that I'm looking for. Why am I looking for two linearly independent solutions? Well, if we go back and inspect the original equation, this is still, even though it's not a constant coefficient problem, it's still a linear second-order differential equation. We are expecting two linearly independent solutions. Turns out one of them is going to be the series generated with all the even values. One will be the series generated with all the odd values. So one will be in terms of C0, one will be in terms of C1. So let's see how that works. We'll generate the even ones from C0 and the odds from C1. And now C0 and C1 are going to be my two separate constants of integration, yielding my two separate pieces of the solution. So basically, and you can use combinations. Again, remember, C0 and C1, you can think of these as our constants of integration. Ultimately, at the end of the day, they will determine what the other coefficients look like based on whatever the initial conditions are for this equation. But in this case, we're just trying to find a general solution. So let's pick the easiest way to do this. Let's associate one set with C0, another set with C1. And by doing that, what we'll do is basically say the following. So in one case, if I let C0 be equal to 1 and C1 be equal to 0, we'll get one set of solutions. And over here, I'm going to let C0 be 0 and C1 be 1, and we'll generate a second solution. Right? This will generate the evens, this will generate the odds, and those will give us our two linearly independent solutions. Okay, so let's start with C0 equals 1. If I know that C0 equals 1 and that C1 equals 0, so I'm just starting with these two assumptions, the next thing I'm going to be able to get is C2. But what is C2 going to be? Well, I'll plug in C0, and we can even use this one here. C2 is just going to be the negative of C0, so it's going to be negative 1. I know that right off the bat, but we could also get it by plugging into this one. right? So C0 is 1, so plug in C0 is 1. K in this case, and just think about what the values of K are. So in this case, this is the value where K equals 0. Right. When K equals 0, I can generate C sub 2. So that's what we're doing. This is the K equals 0 case. So C sub 0, which is going to be 1, is going to look like this. Another way to do it, right? We're plugging in K equals 0, so I'm going to get negative 2 on top. 2 times 1 on the bottom times the original value of C0, which was 1. So this formula comes from plugging into this one, or we could get just negative 1 directly by plugging into this one. Either way. Now we'll look at the K equals 1 case. K equals 1 case is very easy because when K is equal to 1, C sub 1, we already know that C sub 1 is 0. So if I've got a 0 here, it's going to generate a 0 over here, right? 0 times, doesn't matter what this coefficient is, C sub 3 is also going to be 0. So let's go to the K equals 2 case. This will give us C sub 4. So C sub 4 comes by plugging in C sub 2 over here, but we already have C sub 2 is negative 1. So let's plug that in. C sub 4 is going to be, again, I'm plugging in K equals 2. So in the numerator, I'm going to get 0 over, let's see, 4 times 3 times negative 1. So all I've done is plug in K equals 2 into this formula over here, and it gave me this. And what does that equal to? 0. Let's go to the K equals 3 case, and then the K equals 4 case, and so on. So K equals 3 gives us C5, K equals 4 will give us C6, and so on. So what is C5? Well, again, we can see that every other term is generated by these odd ones. So if C1 was 0, if I plugged in 0 for C1, it gave 0 for C3. If I plug in a 0 for C3, it'll give a 0 for C5. So this formula will generate zeros for all of the odd ones. And the second we generate a 0 for one of the terms, all of the ones 2 above that will also be zeros. So look what happens when we get to C6, right? We'll be plugging in C sub basically 4 to generate C6. So imagine we plug in K equals 4 right here to generate C sub 6. Well, I already know this is a 0 because C4 was 0. And so what does C6 have to be? It has to also be 0. And now I know that all the other terms after that, all the odd terms were already going to be zeros, but now that I have C6 equals to 0, C8 will be 0, and C10 will be 0, and that will generate zeros from there on out. So this is going to give me one set of solutions. Over here, we've got a different list. And we'll see why I picked these and set this up this way in a minute. But now we're doing 0 for this, 1 for this. And now we go to the K equals 0, K equals 1, K equals 2, K equals 3, K equals 4 cases, and so on. So come back over here. We're plugging in K equals 0. So when K equals 0, I'll get C0 on this side to generate C2. But if C0 is 0, then C2 is also going to be 0. And if C2 is 0, then down here where we get C4, that will also be 0. And if C4 is 0, then down here where we get C6, that will also be 0. Right? It's basically a recursion relationship gives us the one that's 2 numbers below it. And so the second we have 0 for one of them, the number 2 later will also be 0. And the number 2 after that will also be 0. It makes it easier. This one, though, to generate C3, I can generate C3 from C1. So we're plugging in K equals 1 right here. And we are going to get, when K equals 1, I'm going to get a negative 1 in the numerator. And then I'm going to get 1 plus 2 is 3. 1 plus 1 is 2. So we're going to get negative 1/6. Because this was all times, I'm sorry, all times the 1 that we had from what C1 was, right? C1 was 1. So the number in parentheses is C1, matches up with this number here. We get negative 1/6. We plug in K equals 3. We'll be able to generate from C3 we'll be able to generate C5. So this will give us C5. So plug in C3. We just found C3. It was -1/6. So we'll plug that in a minute. But we're plugging in, this is the k equals 3 case. So when k equals 3, the numerator is +1. The denominator is going to be right here. I'll get 3 plus 2 is 5. Right here, 3 plus 1 is 4. And that's all times the -1/6 that we found for C3. And so what do we get here? We're going to get -1/6 times 5 times 4. 5 times 4 is 20. 20 times 6 is 120. And we could keep generating them, indefinitely thereafter. Again, the even ones will all be 0. The odd ones so far all have factors. And so we get 2 sets of solutions out of here. So our overall general solution is going to be basically y equals c1 times y1 plus c2 times y2. In a sense, you can really think about it as, maybe this is a better way to put it. Well, whatever. Let's leave them as C1 and C2. But basically, y1 is going to be generated from letting C1 or C0 be 1 and C1 be 0. And then y2 is going to be generated from this. This is the easiest combination to pick. And the point being that if you had an initial value problem, you would have to pick values specified by the initial conditions that would satisfy that. But if we're just finding the general solution using 1, 0 and 0, 1 for those 2 values, is going to be the easiest way to do this. So the general solution looks like this, where y1 is the solution that we found over here. What did we generate over here? So this first solution looks like, remember, it's C0 plus C1x plus C2x squared plus C3x cubed, ... Oh, let's zoom in and do that. What did we get for those coefficients in this problem? Here they are. Here's the list of them. C0 is 1, so that number's 1. Plus C1 times x, which was 0, so that term's gone. Plus C2x squared. What was C2? C2 was -1. So -1 times x squared. Plus C3, all the odd ones we already said. We know they're all 0. And then starting at C4, that was also 0. So basically plus 0x to the 4th, and all the even ones after that are going to be 0. So the only 2 coefficients that we have are the C0 and C2 ones. That means these are the only 2 terms that survive. This is the solution. It turns out that this one doesn't have to be infinite. It's truncated after 2 terms, after we get to the order x squared term. The rest are going to be 0. So that's our y1 term. And y2 is the same thing, C0 plus C1x plus C2x squared plus C3x cubed plus yada, yada, yada. Let's get up to, I guess, at least the C5 term, C4x to the 4th plus C5x to the 5th plus ... generated from this. Here's our other linearly independent solution generated from picking this combination of C0 and C1. And this combination yielded 0 for all the even values. So now this term is gone, this term is gone, this term is gone. C1 was 1, so the first term of this is going to be 1 times x, which is just x, plus C3x cubed. What was C3? C3 was -1/6, so -1/6 x cubed. The next term after that was this one, C5, right? C5x to the 5th. So C5 was -1/120th x to the 5th minus ... This one goes on indefinitely, following this recursion relationship and this set of generating values C0 and C1. So here's my y1, here's my y2. y2 is indeed appears to be an infinite series, and those would be the values we'd plug in here, and that would be our general solution to this differential equation. So that's the way that we want to think about these. Again, the hardest part is just understanding, well, the hardest part is doing the algebra And then maybe the hardest part to swallow is right here at the end. Why was I able to pick just 1, 0 and 0, 1 for these values? It would make more sense if we started doing ones with initial conditions, but that gets into a whole nother bunch of wrinkles and difficulties, so I don't want to do that. I just want to end it here. But the reasoning behind it is essentially that we're going to have two unknown constants of integration. I called them C1 and C2 here, but in a way they really correspond to kind of our C0 and to C1. And I could have just left this as, let's just say C0 is, call it C0, and C1 is 0. So in one case, let's just focus on just the terms generated by C0. And all that would have changed is each one of these, instead of having the factor of 1 right here, I would have had a factor of C0. And then down here, I would have had a factor of C0. And then in the next one, I would have had a factor of C0. And I could have factored those C0s out of this and wound up with something that looked exactly like this, right? Factor the C0s out, incorporate those C0s into this constant, and the remaining part of the function would look like this. So the point of picking a 1 here was just to recognize that if I left the constant in here, I would eventually absorb that constant into C1. And so might as well just ignore it to begin with. Similarly, in the second case, this is imagining, let's try to generate the terms that come just from our second constant of integration. What are the terms that just C1 generates? Forget about C0 and think about just C1. If I just called it C1, we would have had C1 and C3 would have been written in terms of C1, right? It would have had a C1 right there. And because that was written in terms of C1, then so would C5 would have been written in terms of C1. And we could have generated written all the way through them, and every single value down here would be in terms of C1. And I would be able to factor all of those out of my polynomial here and factor all those C1s out and incorporate them into this constant of integration. So the easier thing was, instead of carrying them through all the calculations, let's just assume that eventually we'll be able to roll it into this constant that I'm calling C2, and let's just let C1 be equal to 1. So hopefully that's satisfying enough. If you still have questions about that, don't hesitate to reach out. But picking 1 and 0, 0 and 1, this is a viable technique. This is the technique I would recommend to you. The reason we can just pick our seemingly arbitrary numbers they aren't actually arbitrary. We're just recognizing that if we left the constants survive throughout the calculations, it would have made the calculations uglier, and we would have eventually absorbed those constants into these constants anyways. So might as well not even bother. Okay, so this is it. This is all I'm going to give you for series solutions. Again, the homework related to this is going to be just probably 1 or 2 problems. Not going to give you that much, but don't hesitate to reach out if you have any questions.